Okay, welcome back. In the previous video, we introduced the idea of infinite series. We saw an example where that infinite series, sum as I goes from 1 to infinity of 1/2 to the I, that actually converges to a number. So we added up an infinite amount of terms, but it turns out they all just settle into 1. Okay, so we want to talk a little more formally now about what it means to say that an infinite series converges. So we begin by saying let A sub n be a sequence and let S sub n, which is defined to be the sum as I goes from 1 to n of A sub I, be the sequence of partial sums. The sequence of partial sums. Okay, so we're defining S sub n, the nth term of the partial sums, be the sum of the first n terms of A sub n. We then say if the sequence of partial sums converges, then the infinite series, I goes from 1 to infinity of A sub I, converges. Otherwise, it diverges. So the sequence of partial sums converges, then the infinite series converges. Otherwise, if it doesn't, if the sequence of partial sums does not converge, then the infinite series doesn't converge, and we say it diverges. So if that sequence of partial sums does converge, then we say that the infinite series, the sum as I goes from 1 to infinity of A sub I, is equal to the limit as n goes to infinity of that sequence of partial sums. Okay, so that's how we define what an infinite series is. It's limit of the sequence of partial sums. It's the limit of the sequence of partial sums. Now, quick little note on this idea here. If the limit as n approaches infinity of the sequence of the underlying sequence, the A sub n, if that's not equal to 0, in other words, sequence A sub n, that thing does not go to 0, then it goes to anything else, then you got a problem. Because now, as you get towards the end of that sequence, you're adding up a bunch of things that are not close to 0. Okay, it's the things in the AN sequence getting close to 0 that even allows for the possibility for this infinite sum to approach a number. But even if this thing is approaching like 0.1, well, if you have an infinite amount of 0.1s, you have infinity. That's how infinity works. So if the underlying sequence doesn't go to 0, then the infinite series automatically will not converge, right? The infinite series diverges immediately. So if the underlying sequence, the things we're adding up, if they don't go to zero, then the overall thing is going to diverge. However, but just because the limit as n goes to infinity of the sequence of the terms does go to zero, but just because that happens, that does not mean that the series, the infinite series, converges. Okay. It has to be the case that the underlying sequence goes to zero, but that's not enough. It has to go to zero fast enough. We've actually seen that idea in play already back when we talked about our improper integrals. Right? We saw examples where, right, the thing we were doing the integral of, adding up, it got to zero quick enough, right? So therefore, we were able to have a limit. However, there are things like 1 over x which doesn't get to zero quick enough, right? And therefore, that thing diverged. Okay? So we've seen this idea before, right? It has to approach zero, okay? It has to go to zero, the underlying sequence that we're adding up. But what determines whether or not the infinite series converges is how quickly that gets to zero. And we'll see later on some more examples of that.